So today we'll be continuing our study of binomial distributions, and we'll be looking today at sample proportions. So essentially, sample proportions arise from when you take a smaller subset or a sample of a larger population when we're looking at binomial distributions. So rather than, let's say you're on a production line and you're only testing every fifth or so material, let's say you're producing watches and you test every fifth or so watches to see if it's got any defects, then you're only taking a small sample of your larger population and you want to test to see if it has defects or it doesn't have defects. And so you can make claims about that. So the sample proportion is given by the number, the value of the random variable divided by the sample size. So if in this case we're looking at, let's say you had 5 people or you had 5 watches taken from a lineup of 100, or let's say, so you'd have 5 in your sample size, and then let's say one of those watches has defects, so you have 1 out of 5. So in a battery company, a company produces batteries and does annual checks to see what proportions of them are defective. In the last 3 years, the number of defective batteries was as follows: 31 defective out of a sample of 1,500, 19 defective out of a sample of 1,100, and 45 defective out of a sample of 2,000. So now we want to find the sample proportion for each of the years as a percentage to 1 decimal place. So this is relatively simple. It's just using the same formula we had on the previous slide, which was p hat, or sample proportion, is given by x. So the number of successes in the binomial distribution divided by n, which is the total sample size. So let's do that for each of these examples. So this is going to be 31 out of 1,500 for the total sample. And so this is going to be approximately 2.0% when we look at it from this. And so for the next one, we have 19 over 1,100. And this is going to be approximately 1.7% as a decimal when we put this into our calculator. And for this last one, it's going to be 45 over 2,000. And this is going to be approximately 2.2%. So the proportion that are defective isn't that significant. So essentially, these sample proportions are really useful for when we've got a sample. We can determine how many of them match the characteristics we want as a rate or as a percentage of the whole sample we took. And then we can use this sample and we can say that if we do sufficient things to make sure it is, we can then say that this represents the larger whole. So if they've only tested 1,500 watches and we get the sample proportions for those, then we can assume that this sample represents the whole, so we expect 2% of all the watches in the first year to be defective. Or at least that's one way we can do it. But in this example, we're going to use these results to average the defective batteries, because that is only going to improve our results as we're taking it over multiple years, and then we're averaging the results to get a nicer result that is averaged over the years. So what we're going to do here is we're just going to take the average, so it's going to be 2.0 plus 1.7 plus 2.2 all over 3, and this is going to be approximately 2.0%. So approximately 2% of the batteries are defective within all the samples we took. So from here, we can assume that 2% of the batteries produced will have defects. And this is a great way to look at trying to reduce those. So you might then look at, oh, well, what are we doing that's having issues with these batteries, and how can we reduce these defects in the sample proportions and thus in the larger group. So moving on, so then we have central limit theorem, which is for larger sample sizes, the sampling distribution of the sample proportion is approximately normal. So essentially what this is saying is if we have a larger sample, then the sample proportion is going to be normal, meaning that it's not going to, there's nothing affecting it. It should just even out and be approximately the same as the larger population. So essentially what this is saying is that as we increase sample size, we more closely approximate the larger group. And so this is really useful because if you have a really large sample size, you'll get a much better picture of what's going on in the large group, which is why studies usually have sample sizes of multiple thousands. Whereas if you were to just take 10, your sample size would be very small. So your sample distribution is more likely to not be normal, meaning it's skewed by some other factors that are affecting it that aren't affecting the larger population. Now looking at the mean and variance. So the expected value of the sample proportion, or the mean, is given by the percentage that, sorry, the probability that we get a success in the larger group. So this is pretty much just the same as your Bernoulli distributions, but then for variance, we're going to get it's the probability of success times the probability of failure divided by our sample size. So moving on to using those, find the mean and the variance and standard deviation of the sampling distribution with the probability of success being 0.4, and with 50 trials, and the probability of success in this one, 0.9, and the sample trials of 125. So if we look at this, then the expected value of the sample proportion is going to just be 0.4 because it's the probability. Meanwhile, the variance of the sample proportion is going to be given by 0.4 times 1 minus 0.4 divided by 50. And if you put this into your calculator, then you should get that this is approximately, this is approximately 0.0048. And meanwhile, for this one, we have the expected value of P is going to be 0.9, while the variance is going to be just a little bit more complex, as it's going to be 0.9 times 1 minus 0.9 all over 125. So now just substituting this into your calculator, you should get that this is approximately 0.00072. So this is approximately 0.5%, whereas this is less than 0.1%. So if you look at these, then the variance of our sample proportions is actually going to decrease as we increase our sample size. So essentially, we're going to get a more accurate or a less distributed value if we increase our sample size sufficiently, and we can really start to get this variance down to very small numbers, which means we're getting a more reliable result as it's less spread out, it's less varied. So this is similar to the central limit theorem, in that as we increase our sample size, we more closely approximate the larger group, and this is essentially what's happening. So as we increase our sample size here, we're reducing our variance and getting a more accurate answer. So moving on, so the incidence of asthma in a particular population is 21%. A sample of 89 people was taken from this population. So how many people in this sample would you expect to have asthma? So in this case, what we're going to do is we're going to go 21% times 89. Now, why am I doing this? Because if we assume that the sample proportion of people has approximately the same rate of asthma as the larger population, then we can assume that 21% of the 89 people has asthma. And this is approximately 19 people. And we're going to use this to find the sample proportion as a fraction. So now if we want to find the sample proportion, it's just going to be P is equal to X over N. And so we expect 19 people to occur, and we have 89 total, so we should get 19 over 89. Now, if you want to find the mean and the variance of this, you can do that using the sample size and the expected probability of having asthma in the larger group. So that importantly, that is from the larger whole, not so much the sample size in particular. So but if they say this is the probability of this event happening in the sample size, then you use that as your p-value. Anyway, so what did we learn in this lesson? We learned about what a sample size is, how it relates to the larger population, and how to find the mean and the variance of the sample proportions. Anyway, I hope that this was helpful, and I'll see you guys next time.